Hello, good afternoon, everyone. I hope you are all well, and welcome to the Introduction to OxTS GX-IX Technology webinar. As Rob mentioned, we will have some time for questions at the end, so please, if you have any, do submit them, and we will try to get you some answers after the presentation. So, OxTS GX-IX technology is a trademark proprietary technology of OxTS, and it is basically a tight coupling algorithm used by our navigation engine. In this webinar, we will go through what GX-IX is, so the functioning principles behind it. We will mention a few good reasons on why to use GX-IX. That's in short performance improvements in bad GNSS, but we will see more in details. And also we're going to have a few notes on what else you can do with GX-IX by enabling a few post-processing options. So what is it? We will shortly look at definitions of GNSS only, loose coupling, and tight coupling. We will look at what GX mode and IX mode separately do, and we will mention some compatibility aspects for the algorithm. GNSS only. Very shortly, just to mention that basically it's not good enough. In a challenge GNSS environment, such as a city, you can have non-existent or very noisy data from the GNSS. You have a limited data rate, typically maximum 20 Hertz, and increasing the rate on GNSS usually only gives you increasing noise, so not beneficial. And also using just GNSS only data, it can be difficult to account for changes in the orientation angles, heading, pitch, and roll. You will certainly need 2 or 3 antennas, and even by doing that, it won't be enough, because in order to account for these changes, the receiver, GNSS receiver, will have to be able to use satellites that are very low on the horizon, so they can better account for difference in vertical position. But obviously, in a challenged environment with a lot of obstacles around you, you are very unlikely to be able to see satellites that are low on the horizon. And on the right, I've just included as an example, a typical GNSS only data that you can have in a heavily dense urban environment. This is New York City. Okay, so having said that GNSS only is not good enough, the solution is basically to couple the GNSS solution with an IMU solution. And there are 2 ways of doing that, so-called loose coupling and tight coupling. In the case of a loose coupling solution, what you have is basically 2 independent solutions, the GNSS and the IMU one. So position of the system will be calculated by a GNSS receiver, and at any given time, the receiver will require at least 4 satellites to give you a position fix. Fewer satellites means the receiver is not able to compute a position fix. What the IMU does, in addition to providing acceleration and angular rate data, which can be used for the orientation bit, as we said, the GNSS only can struggle with that, it can also provide position and velocity in between GNSS updates. This basically includes 2 things. One is the standard operations of the system, so meaning when you have regular GNSS updates, but because the frequency, the output rate of the system is much higher, say 200 Hertz, than the rate of the GNSS receiver that can be 2 Hertz or 10 Hertz. So in between GNSS updates, the data that the system is able to calculate for position and velocity is obtained thanks to the IMU. And the other way the IMU fills in is during GNSS outages. So you can have a few seconds or few minutes of no GNSS data. You will still have a position solution thanks to the IMU. The tight coupling. In this case, you have a proper one integrated solution. What GXIX does is ignoring the receiver's solution and rely instead on the raw observables, so pseudo-range, Doppler velocity data from the satellites. And instead of calculating the navigation solution based on GNSS only data, what it does is integrating the data from each individual satellite into the IMU solution. By doing this, it is properly blending GNSS and IMU data together in one. And another great benefit is you can still have a position mode and velocity mode available even with fewer than 4 satellites. GX and IX. So GX mode operates when you have at least 4 satellites. So similar in this to the GNSS receiver. But it works differently. As mentioned, it doesn't calculate the position just from the GNSS data, but by integrating, merging GNSS and IMU data together. And what it does is checking the GNSS data and the IMU data against each other in order to figure out what the real motion is and hence what the real solution is. We will see examples of this later on in a bit. The IX mode operates when you do not have enough satellites available for a given mode. So for SPS, for example, that's 4 satellites, as we discussed. That's the minimum required for a position fix. But if you are looking at higher position modes, such as RTK, then you need at least 6 good satellites. So again, IX can give you RTK level even with fewer than 6 satellites, which is something the receiver cannot do. The way it works is by providing single satellites observation as an aiding. Since you do not have enough satellites for a full position fix, full position solution, you can still use, thanks to IX mode, single satellites data as an aiding to the IMU solution. So pretty much as if you were using a wheel speed sensor, for example, that would help the IMU velocity solution, you can use single satellites data as an aiding to the IMU. And in addition, it has this partial position solution that is constrained by inertial measurements, which means the uncertainty around this solution is highly limited, unlike the GNSS receiver. Again, we will see examples of all of this in a bit. The navigation engine decides when to use GX and when to use IX. It switches intelligently between them, depending on 2 things. Yes, the number of available satellites, as we discussed, but also on the quality of the data, because having a given number of satellites doesn't mean that you are fine, you are okay. The data from these satellites needs to be suitable, appropriate for the mode that the system want to achieve. So examples. If you have 6 good satellites, the system can be in GX RTK mode. Obviously, you need differential corrections as well, not just the satellites data. But if you had 4 or 5 good satellites, as we said, for RTK, you need at least 6. So you could fall back on GX DGPS, but the system can use those satellites to provide you with IX RTK if the data was good enough. So even with fewer than 6 satellites. If you had 2 or 3 good satellites, then obviously the GX mode is not available. Like we said, it needs at least 4. You can still have IX RTK or IX DGPS. So not just a basic IX SPS mode. This is what you get if you had 2 or 3 bad satellites, barely enough to have a position that is in SPS mode. But if the data was good and corrections were flowing through nicely, you can even get, differential DGPS mode or RTK mode, even with, that many that fewer rather satellites. So basically what the system does is giving you the highest possible position mode at any given time. And this will have a huge impact on overall position accuracy. Examples in a bit. A word on compatibility. So GXIX is available with all OxTS units, regardless of the GNSS receiver they are mounting. That is because, as mentioned, it relies on raw GNSS data. It doesn't care about the GNSS receiver calculations. All it needs is raw observables. It is available in real time or post-processing, which means if you did not have it in real time, you can enable it in post-processing and the other way around. You can collect data in real time in GXIX and then reprocess the data to see the difference in post-processing. It is compatible with GPS satellites in all modes, SPS, DGPS, and RTK. It is compatible with GLONASS satellites in SPS and DGPS, and it is partially compatible with GLONASS in RTK mode. Partially means it will depend on the type of receiver that you have on the base station end, the base station that is providing differential corrections required for RTK mode. That needs to be compatible with the receiver installed on the unit. And we are working towards a full compatibility, same as the GPS satellites, so you don't have to worry about what kind of receiver the base station has. It is currently not compatible with Beidou, but it's being implemented to be compatible with Beidou. And finally, it is not compatible with SBAS corrections. SBAS can only be used with GPS satellites anyway, and it's not compatible with GXIX mode. Okay, so why use GXIX? In short, that's performance improvements in bad GNSS environment. More specifically, it does checks on GNSS data, rejecting those GNSS updates that are not suitable. It can provide a position mode with fewer than 4 satellites, so the system doesn't go completely blind. It has a faster inertial relock, meaning when the number of satellites come back to 4 or more, so a full position solution is available again, GXIX is much quicker than the receiver to jump back to that full position solution. So it provides longer period of times in better position modes because it always gives you the best position mode available at any given time. Examples of all of this. First, the checks on GNSS data. In loose coupling, or what sometimes we call receivers mode, position is calculated by the receiver. So if a wrong GNSS update comes in because of multipath, for example, the signal, GNSS signal being deflected by obstacles, buildings, trees around the system, this will cause the position to jump. GXIX, though, doesn't believe the GNSS data straight away. It checks it against the IMU data. So if the change in position reported by the GNSS is not matched by a motion detected by the IMU, the system will reject the GNSS updates. And in addition, it will rely on GNSS only if the signal is of high quality, meaning it has a higher CNR, carrier to noise ratio threshold. So only if the signal was of a given strength and quality, it will be used in determining the position solution. This is an example on the ground. So down here on the left, you can see the red trace is the GXIX mode, whilst the blue one is the receivers mode. So this is the same data processed twice in GXIX and in receivers mode or loose coupling. So in this case, the vehicle was stationary at a traffic light. And while it was waiting, a GNSS update came in that was basically wrong because of multipath. So you can see that the blue trace has a jump to the left of about 1 meter. The red trace, though, doesn't show this jump. So the GNSS update was rejected because the IMU did not detect any motion. So the system did not believe that the GNSS update was genuine. You can see that the trajectory of the loose coupled solution stays wrong around the corner, and just later on, that's a couple of 100 meters down the road, finally in this open bit, where you have fewer trees, a correct GNSS update comes in, and finally the receiver solution jumps back to where the GXIX one has been all along. So that's an example of how the system rejects wrong GNSS updates and keeps the correct solution. Second thing, having a position solution available even with fewer than 4 satellites. The receiver, as mentioned, is not able to calculate that with fewer than 4. It is completely blind. So having 1 or 2 or 3 or 0 is basically the same. IX mode will use whatever data is available from satellites as an aiding to the IMU solution. So the satellite's data is not completely wasted. It can allow the system to maintain a position mode. And this will limit the drift that you have in GNSS outage hugely, and hence improve position accuracy. So a couple of examples on this. In this graph, you can see red is GXIX mode and blue is receivers mode. Solid lines are position modes, and dotted lines are position accuracy. The dark green dashed line is number of satellites available. So you can see that the receivers has no position mode 0. That is because the number of satellites available are fewer than 4 most of the time. It tries to jump back to a position mode, but very shortly, and then it goes back to none. During all of this time, IX mode is kicking in, and it guarantees IX-SPS mode, which is way better than going completely blind. And as a result, you can see that position accuracy stays at a decent level. We are around 1 meter in this case, whilst the position accuracy for the receiver drifts away up to more than 20 meters. Situation on the ground, that was an urban canyon in between buildings. Direction of travel is from down here on the right and then turning left and in again. So in this bit here, you can see that the red line, GXIX, is solidly and sensibly on track, whilst the blue one is drifting and basically hitting a building here. And as soon as finally the system goes out of the urban canyon, the receiver is able to catch those 1 or 2 more satellites that allows it to go back to a more sensible solution slowly. Again, where the GXIX solution has been all along, even in between buildings in an urban canyon with fewer than 4 satellites available. Another example, it's similar to the previous one. Again, you can see that no mode is available for a long time here. You can see that it tries basically to go back when it manages to track 4 or more satellites, but the number of satellites used, that's the dark green line, shows us that even if the system is able to track 4, just 2 of them are being used because the other 2 are too bad basically to provide a solution. And this causes the receiver's mode to jump back again to 0 and again and again and again. It doesn't have a solid position mode. During this time, IX mode doesn't just give you IX, which is these lines here, but it's even able to go to IX DGPS. You see this higher steps here. And for very short time, even to IX RTK, that's bit here. So even with fewer than 4 satellites, you do not just get basic IX SPS, but depending on the data, you might even get better than that. And this is reflected again in position accuracy. This is the dotted red line is GXIX position accuracy. That's about 40 centimeters. This is half a meter here. So that's about 40. And that's with 2 satellites available. Whilst the position accuracy of the receiver is drifting up to about 5 meters down here before it comes back when some data comes back here, but it stays at a higher level than the position accuracy for GXIX mode. And that's the situation on the ground. This is not as bad as the previous example I've showed you, because you have a slight opening on this side. Nonetheless, the receiver mode is drifting to the left and going over the grass, while the GXIX one is solidly on track. Okay, faster inertial relock. What does it mean? So when the number of satellites is back to more than 4, so the receiver can calculate a full position fix again, it will take time to do that because it will start from scratch. With fewer than 4 satellites, the receiver has no clue basically what its position is. It could be in the UK, in Italy, like the dataset I've showed you, in Japan, in Brazil. It has no clue. The IX mode does have a clue, because the position, as we said, is constrained by inertial measurements. So while it cannot be extremely precise to the centimeter level, say, the search area, uncertainty area, will be in the meters. So it will be much quicker to resolve ambiguities when it gets more satellites data. So the system will be able to calculate a full position much quicker. Not just that, but because it gains the position more quickly, it will be able to jump back to higher position modes if available, if corrections were available, again, much quicker than the receiver does. So it means that the system will drift much less and have a better position accuracy. And here is an example. You see, at the beginning, this is the dark green line is number of satellites available. And as you can see, it is dropping, quickly dropping to 0. So when it does, both GXIX and the receiver will have no position mode, 0, because no satellites at all are available. Okay, not even 1 or 2, nothing. But as soon as satellites come back, just 4, just the minimum required, you can see how GXIX is very quick in jumping back to IXSPS, to a sensible position mode. The receiver instead will take some time, to calculate its position fix from 0, from scratch. And during this time, its position accuracy will keep drifting. This is position accuracy, again, the 2 dotted lines, and initially they are drifting together in a similar fashion. But as soon as GXIX relocks, you can see that position accuracy stops drifting and it becomes more solid. At this level, we are looking at about 30 centimeters here. The receivers instead has its position accuracy that goes on and on in its drift. So it gets worse and worse, up to more than a meter. So that's an example of what quicker inertial relock can give you. Okay, 2 examples of use cases, tests that we've run. The first one was done in Paris. In a very dense urban environment, a lot of obstructions, a lot of multipath, poor satellite visibility, and fewer than 4 satellites for 20% of the data. The results were that the receiver solution was in no position mode, no solution at all, basically, for 36% of the time. GXIX was with no solution for just 14% of the time, both real-time and post-processing. So that's the impact on performance, that the ability of GXIX to hold on to a position mode, the impact that it can make. And this obviously translates into a much better position accuracy. If you look at the error, horizontal and vertical error, you can see that it's way smaller. And if you post-process the data, not just collect it in real time using GXIX, but post-process it using our combined processing, then the results are even better. But even just looking at the real-time performance, you can see, vertical error is twice as much and horizontal error is 4 times in receivers mode. Second example, in this case, we passed with our vehicle underneath a bridge several times. So we've done multiple loops up and down, to have a long sequence of brief but very severe obstructions. Brief because the time to pass underneath the bridge is few seconds. Severe because you completely lose the GNSS, 0 satellites. So you have to start from 0 availability, meaning the receiver will have to start from scratch, but IX mode, like mentioned, will have the position constrained by inertial measurement, so it is much quicker in jumping back. So the results are that no solution for the receiver was for 1.7%, while GXIX is 0.5. But the biggest, I would say, impact is on how quick the system was to jump back to the highest possible mode, that's RTK. The system was 94%, 0.5, 0.6% of the time in RTK, whilst the receiver was only 84.5. So it's 10% more time in RTK because of the faster inertial relock. And again, if you look at the position accuracy, the horizontal error is 4 times as much, and the vertical one is again twice as much in the receiver's mode because of the longer time that takes the receiver to go back to RTK. Finally, a few words on a couple of things that you can do by enabling the GXIX algorithm in post-processing. Basically, you can disable or modify differential corrections that you had in real time. You can apply RINEX files, and you can have the possibility of analyzing your GNSS data. So first of all, this is how you enable GXIX, either in real time or in post-processing. That's in the Advanced Tools GNSS Control section of navconfig. The way you act on differential corrections that you had in real time is thanks to the fact that the GXIX algorithm uses raw data. So in the case of the receiver, whatever GNSS data you had, including differential corrections, that is, unchangeable, cannot be modified in any way. You've logged that data, and that's it. GXIX instead, it will take only the raw data, and you can, remove corrections if you wanted, or modify them or apply other corrections. So for example, if you had SBAS in real time, you can remove that. Say you wanted to gauge and measure the impact that differential corrections are making to your data. So the best way is to process your data with and without corrections, or with different type of corrections. This is possible thanks to GXIX. You can remove n-trip or base station corrections if you had them in real time, or you can leave them, but you can modify the datum that you have set for those corrections. If you realize that that was wrong, for example, you can edit that and modify it. The data is not wasted. If there was an error in real time, you can still recover it. And most importantly, you can use RINEX files for corrections to improve your accuracy. So you remove whatever real-time corrections you had. Say, for example, you had some interruptions in the flow of corrections. That would cause, obviously, a loss of position accuracy, because if you lose the stream of corrections, you will lose some position accuracy, obviously. But this doesn't happen with RINEX files. It's similar to applying a custom flow of corrections. So you can replace real-time corrections with RINEX files in GXIX mode. And another thing that you can do is enabling a special processing mode that our software allows you to enable in GXIX mode, and extract the raw GNSS observations for each tracked satellite. And then you can complete, we have internal tools, or you can have your own, complete some CNR analysis and tracking plots. So you have a better understanding of what your GNSS data was, and that can be useful in troubleshooting and basically understanding, for example, exactly in what portions of your trajectory you had issues, and what kind of issues, and how many satellites you had, and what was the CNR, and so on, for all your GNSS data. Thank you.
Thanks, Sam. We've had a few questions come in. So the first one, basically just asking, can I get GXIX corrections anywhere, or is it limited to certain locations? I'll let you take that, but I can jump in if you like.
No, it is not. The corrections that GXIX does use are the same as what the receiver uses. So it's the same N-trip corrections, say, or base stations if you have a field base station. So it's the same kind of corrections. The only corrections that can't be used, as I mentioned, they are not available, not compatible with GXIX, is S-bus corrections. Other than that, the corrections are exactly the same. Okay.
There's a question, does GXIX come as a default with RT, or is it a buy-on sort of additional option? And it depends which product you go for. For the vast majority of our products, it comes with it. This is a standard product. On some of our very cheaper products, so things like the XNav, some of the more survey-oriented products, it is an option on some of those. But generally, most of our products, the RT is available just as a standard feature.
Yeah, it's just we have two levels basically of GXIX. So the one that the level 1, say, that can get you GX differential or GX DGPS, and the higher level that can get you a GX RTK. So level 1 is always available, and it also depends on the kind of like Rob said, of unit that you have. Most units will be will have level 2 as well available.
Okay. There's a question asked, should we always use GXIX, or what would be the reasons not to use it?
So the only reason is, like I mentioned, you have a partial compatibility with GLONASS, depending on basically the receiver at the base station end. So if that base station was compatible, meaning you could use GLONASS satellites all the way to GXRTK, then there is no reason not to use GXIX algorithm, especially in urban environment. If the base station was not available, which means that you cannot use GLONASS in GXRTK, you can use it in GXDGPS, not in GXRTK, then you will have to evaluate if the number of GPS satellites are enough to give you GXRTK. So that's the only reason that you say temporarily have, because as I said, we are working towards a complete across the board compatibility with GLONASS and with Beidou. But until then, say, that's the only caution that you can have. We have introduced in latest firmware versions the mixed mode. So basically you leave it to the system to figure out whether it should be using a receivers mode or GXIX mode. Okay, so if you wanted some peace of mind, if you wish, you can enable mixed mode and leave it to the system. So whenever you do not have enough satellites to give you GXRTK, the system will revert to receivers mode, and if possible, if the data does allow for that, you can have RTK integer instead of GXRTK. If you have an older version of firmware that doesn't give you mixed mode, I would recommend you use GXIX in urban environment. Absolutely. While if you are on a say testing ground, open sky environment, then you are fine to use receivers mode, because in that case, obviously, receivers mode is relying heavily on GNSS data, which can be bad in urban environment, but it will be good on a testing ground. So it is okay to use the receivers mode in that case.
Okay. If you are on a proving ground or in open sky conditions, is there any difference in performance between GXIX and receiver mode?
No, there isn't. They are basically as good. Like I've just mentioned, the problem that you might have with the GXIX mode is that if the base station was not compatible with GLONASS, you might have fewer satellites for GXRTK mode. Remember that you need at least 6. And for GXRTK, you could only use GPS, not GLONASS satellites in that case, if the base station was not compatible. But on an open sky environment, such as a testing ground, you are very likely to have plenty of satellites. So even just GPS satellites, you might even not have GLONASS on your system, just have GPS satellites, they will still amount to 8 or 9 or 10 satellites. So more than enough to give you GXRTK mode. Okay, so basically there is no reason not to if you wanted. It's they thing is they are equivalent. Okay, there is no real difference between them. Whilst in urban environment, GXIX is better than the receivers mode. Okay.
Are there any other settings or things that can improve performance in an urban setting besides just switching to GXIX?
Sorry, could you repeat the question, please, Rob?
Yeah, so are there any other settings, things you can configure in the software that can improve performance in difficult urban environments besides just using GXIX?
Yes, absolutely. So it would be long to go through all of them. So last month we've run another webinar specifically on advanced settings for challenge GNSS environment, and the recording is available on our website. So if you are interested, I do recommend you go and check. That's on the Resources Hub. You can find the link to that webinar, and it contains a lot of settings, of advanced settings and hints on how to use the system in challenge GNSS environment. Okay.
For the question which I can quickly take, are you planning compatibility with Galileo? And essentially the short answer is yes. The long answer is that whilst at the moment there is a difference between which constellations you can use for GXIX versus receiver mode, the only practical difference between those is that it takes our development team time to implement all the different constellations and the different message structures and so on of the different satellites into GXIX. So we're currently working on Beidou simply because it's a larger constellation. There are more satellites physically up there than with Galileo, but as soon as we've finished that, we'll be working on Galileo as well. So ultimately the plan is to have just as many satellites as you can see in receiver mode available with GXIX as well.
Yeah.
There's another question about mixed mode, specifically if it's receiving data from a constellation that isn't compatible with GXIX, such as Beidou, would that be more likely to cause it to switch to receiver mode, or is it down to other factors as well?
No, it's down to other factors. So it's not the fact that you are tracking Beidou. Obviously, if you are in GXIX mode, like I said, it's currently not compatible with Beidou, so it won't use Beidou satellites. But the fact that the system is receiving Beidou won't be the reason why it would switch to receivers mode at some point. What would happen is, for example, if the system did not have enough satellites in GXIX mode, so it wouldn't be able to guarantee, say, GXRTK, and the system, we have an internal logic that checks at real time what sort of position mode, receivers mode, and GXIX mode can give you. So if GXIX mode was giving GXDGPS and receivers mode was giving RTK because of the different number of satellites, then it would switch. So to stay with your example, say for example Beidou, say you had GPS and Beidou on your system. Okay, so Beidou satellites won't be available in GXIX mode, and say you are tracking 6 GPS satellites and a number of Beidou. 6 GPS satellites would be enough to give you GXRTK. If at some point you lose a couple of satellites, of GPS satellites, because you go into a challenge environment, say, under some trees or something like that, so the system will not be able to give you GXRTK. At the same time, receivers mode, because it has those 4 GPS satellites, but on top of that, it can have, say, another 4 Beidou, so 8 altogether, it might be able to provide, depending on the quality of the data, but it might be able to provide RTK integer. In that case, the mixed mode will allow the system to switch immediately to receiver's mode and give you RTK integer. As soon as you get those two GPS satellites back, so GX RTK mode is available again, the system can switch back to GX RTK, okay, depending on which one would be better at any given time. Okay, so Beidou affects it in the way that receiver's mode will have more satellites available than GXIX mode currently. Okay, like I said, we are working towards implementing Beidou with GXIX, and then you wouldn't even have this difference. Okay.
Thank you. Lastly, there was another question about how GXIX affects the drift performance. Is there any real difference between GXIX or receiver mode in an environment where essentially kind of, for example, heading performance, if, for example, you have a single antenna system and the vehicle has been stationary for a little while and the heading would start to drift, would that be any better with GXIX?
Not if you do not have, no GNSS updates at all. Okay, because that's so if you are in complete outage, then both modes will be only relying on the IMU data, and there is no real difference because like I've described, GXIX acts on GNSS data in a different way to what the receiver's mode does. But if you have no GNSS data at all you have is IMU, and there won't be any difference. But if you had some GNSS data, so that can be two things, as described in the presentation. Either you have fewer than 4, and in that case, yes, IX mode can use whatever data you have, improving your accuracy, while the receiver wouldn't be able to do that. 2, in cases where you have more than 4 satellites, so even the receiver can give you something, if the GNSS data is troubled, and it can give you wrong data, affecting your position, affecting your heading, GXIX will check it against the IMU, and if the motion that the GNSS is claiming is not matched, it doesn't correspond to something that the IMU has detected as well, GXIX will reject that update. Like I've showed you that slide where the system jumped to the left by 1 meter in receiver mode, and it didn't do that in GXIX mode. So that's precisely an example of what you were describing. Questionable GNSS updates will be rejected by GXIX mode, whilst the receiver would accept them instead. And obviously this will have an improvement on your position and your orientation data. Okay.
Just time for one quick one. I think you mentioned it earlier on, so if you don't mind going back to the slide where it was, could you show us where the option is in nav config to switch between GXIX and receiver mode again, please?
If I can find it again, here we go. Okay, so that's in the advanced tools GNSS control section, where you can see you have 3 options. One is receiver's calculation, so the loose coupled solution. One is GXIX, raw data processing, and one is the mixed mode. Mixed mode is only available if you have a firmware that is at least from 2019 or later. Okay, with older firmwares, the mixed mode option will not be available. Okay.
Okay. I think that's all the questions. Thank you very much for your time and for the very interesting content, Sam. Thanks everyone else for your time for joining us. We'll be doing a few more of these on various topics throughout this month and next month. Hopefully you'll be around for those as well. This is being recorded, and you should have a link to the download of this. So anything that you missed or you want to go back through, you should be able to do so. And any questions we didn't get around to asking, please well, we'll go through, but if you have any further questions that you didn't get around to asking here, please send them to other supports or also sub, and we can look at those later. But I think I make that 4 o'clock. So thank you very much for your time. And
thank you, everyone. Yeah, thank you, everyone. Have a good day.